In this video, I will talk about parallel RLC circuit. I will show you the derivation of admittance equation of parallel RLC circuit. Finally, I will draw the admittance diagram for three different cases in case of parallel RLC circuit. See, this is our resistor R, this is inductor L, and this is the capacitor C. One end of this R, L, and C are connected at this point. Another end of R, L, and C are connected at this point. So this is our LC parallel circuit, which is connected across a sinusoidal voltage source. As this is sinusoidal voltage source, the instantaneous voltage equation will be Vt equal to Vm sine omega t. Let's say in this circuit we are applying the sinusoidal voltage, therefore the RMS phasor of applied voltage, RMS phasor of applied voltage is V vector, which is equal to V with phase angle 0 degree volt. Now see, as the maximum value of applied voltage is Vm, therefore it will be Vm over root 2 with phase angle 0 degree. Sorry, here it will be 5V, initial phase of the applied voltage. Here 5V is equal to 0. Let's say the total current is I, therefore the total current phasor is I vector, which is equal to RMS phasor of total current. Now see, in this branch we have this resistor R, in this branch we have this inductor L, and in this branch we have this capacitor C. Therefore this branch impedance will be ZR. ZR will be equal to R phase angle 0 degree, unit will be ohm. In this branch we have this inductor, therefore the impedance will be ZL equal to JXL or J omega L ohm. In this branch we have this capacitor, therefore the branch impedance will be ZC, which is equal to minus JXC, where XC is equal to 1 over omega C. So ZC is equal to minus J over omega C. Now see, in this branch we are applying the voltage V, in this branch we are applying this same voltage, and in this branch the voltage is V. Therefore the current IR will be equal to voltage over impedance of that branch, which is ZR, or V over R phase angle 0 degree. IL equal to V over ZL or V over J omega L. IC will be equal to V over ZC or minus JXC. In the circuit, if I denote this node as node A, you will see this current I is entering, and IR, IL, and IC will be outgoing. Therefore, if I apply Kirchhoff's current law at node A, apply KCL at node A, you will see incoming current I will be equal to the sum of outgoing currents IR, IL, and IC. I equal to IR plus IL plus IC. We know that IR is equal to V over R, IL is equal to V over JXL, and IC is equal to V over minus JXC. See, here we have this plus sign. We can break down it into like this: minus into J square. We know that complex operator J square has a value of minus 1. So minus 1 into minus will be plus. So in the next line I can write I equal to V over R minus J square into V over JXL. Here we have this minus 1. Minus 1 is equal to J square. So I can write it like this: plus J square over JXC into V. Okay, now see, in the next line I will get I equal to V over R minus J V over XL plus J V over XC. If I take V common from all the terms, I will get 1 over R plus J over XC, or if I put XC is equal to 1 over omega C, you will see I will get omega c minus 1 over xl, or instead of xl I will put 1 over omega l. From the definition of inductive susceptance, which is equal to BL, we know that BL is equal to 1 over XL or 1 over omega L. And from the definition of capacitive susceptance, we know that BC is equal to 1 over XC, and we know that XC is equal to 1 over omega C. So BC will be equal to omega C. So this 1 over R will indicate the conductance, omega C will indicate the capacitive susceptance, and this 1 over omega L will indicate BL or inductive susceptance. So if I put G, BC and BL in the next line, I will get total current I is equal to V multiplied with G plus J BC minus BL. Therefore we will introduce a new term, admittance, which is expressed with Y, and this Y will be equal to G plus J BC minus BL in case of parallel RLC circuit, and the total current equation will be I equal to V into Y. Okay, now see, the Y is the complex admittance of the circuit, where G is the conductance. This G is the conductance, which is the reciprocal of resistance. BC, this BC is the capacitive susceptance, which is equal to 1 over XC or equal to omega C, and BL is the inductive susceptance, which is equal to 1 over XL equal to 1 over omega L. So finally we can write down the complex admittance of the RLC parallel circuit will be equal to Y equal to G plus JBC minus BL. This is known as the rectangular form of the admittance equation of parallel RLC circuit. If I take the magnitude of Y and admittance angle, I will get Y equal to root over G square plus BC minus BL whole square, and phase angle will be tan inverse BC minus BL over G. Okay, this is known as the polar form of complex admittance of parallel RLC circuit, and I deduced the rectangular form of complex admittance of parallel RLC circuit. Now I will show you how to draw the admittance diagram of parallel RLC circuit. Before drawing the admittance diagram of parallel RLC circuit, let me recall the admittance diagram of parallel RL and parallel RC circuit. See, in case of parallel RL circuit, the admittance equation Y was equal to G plus JBL, G minus JBL, and in case of parallel RC circuit, admittance Y was equal to G plus JBC. We usually draw the conductance G in the direction of plus x-axis, so this will be our G. Here similarly G will be in this direction. See, this is minus JBL, this is imaginary axis, this is plus J, this is minus J. So as this is minus JBL, therefore we will draw minus JBL in this direction. Let's say this is minus JBL. Similarly here, this will be our plus J axis and this will be our minus J axis. As this is plus JBC, let's say this is that plus JBC, plus JBC. Now see, to draw a parallelogram, we will draw two additional phasor quantity or vector. One is from this point, another is from this point. This one will be the equal vector of the minus JBL, and this one will be the equal vector of G. Therefore, you'll see if I join this point and this point, or if I go directly from this point to this point, I will get the diagonal of this parallelogram, and that diagonal will indicate the admittance Y. Okay, now see, if I go from this point to this point, then this point to this point, that will be G minus JBL according to the formula of vector addition. Then if I go directly from this point to this point, that will be equal to Y. Okay, or if I follow this way from this point to this point, then this point to this point, that will indicate the same thing. Okay, now look here, this is plus G. If I draw an additional vector from this point, that will be the equal vector of plus JBC, and an additional vector from this point, that will indicate the conductance G. Then if I join from this point and this point, or if I go directly from this point to this point, that will indicate the admittance Y. Now see, here the admittance angle was phi, which was positive, and here the admittance angle phi, which was negative. This angle is the angle between the real axis to admittance line. Okay, see, now see here, if I go from this point to this point, then this point to this point, that will indicate G plus JBC. Then if I go directly from this point to this point, that will indicate the admittance. Okay, similar case is applicable here. From this point to this point, this is plus JBC and this is G, then this will indicate the Y. This is the diagonal. Okay, now see, in case of parallel RLC circuit, the admittance Y is equal to G plus J BC minus BL. If I break down the quantities, I can write it like this: G plus J BC minus J BL. Now see, as the imaginary part is the difference between BC and BL, there are three possible cases. The first one could be BC could be greater than BL. Second case is BL could be greater than BC. And third case is BL could be equal to BC such that this term will be equal to 0. That means the admittance will be G. So I will show you three possible cases. While drawing the admittance diagram, you have to remember that we will draw the conductance in the direction of plus X axis. We will draw plus JBC in this axis, and we will draw minus JBL in this axis, because this axis indicates the real number, this axis indicates plus J axis, and this axis indicates minus J axis. After drawing JBC or JBL, we will draw parallelogram by drawing the equal vectors, and we will get admittance diagram of the RLC parallel circuits. So out of three possible cases, at first I will show you the case when BC is greater than BL. Our admittance Y is equal to G plus JBC minus BL. So at first we will draw the conductance G in the direction of plus X axis. Let's say this is plus X axis, and in this direction we are taking the conductance G. This is our conductance G, and from the neat sketch you will see I have indicated G with vector OA. After that we will draw BL, as this is minus JBL, so I will take minus JBL in this direction. From the neat sketch you will see I indicated this JBL with OB. After that I will draw plus JBC. From neat sketch you will see I indicated JBC with OC. Now see, at this point we have two vectors are operating in opposite direction, therefore the resultant will be BC minus BL, as BC is greater than BL, therefore the resultant will be in this direction. Let's say this is that plus J BC minus BL. Okay, from the neat sketch you will see I indicated that with OD. Now see, to draw a parallelogram, at first I will draw an equal vector from this point, and I indicated that with DE, and DE will be equal to OA. From this point I will draw another equal vector, and that equal vector will be equal to AE, that will be equal to BC minus BL. Okay, now see, if I draw the diagonal of this parallelogram, you will see I will get this, and this will indicate the admittance, because from this point to this point we have this G, and from this point to this point we have plus J BC minus BL. Or if I follow this way, plus J BC minus BL, then this is G, then the diagonal will indicate the admittance. See, this is the neat sketch. You will see the angle between the admittance Y and the real axis is phi, and here as BC is greater than BL, therefore this phi will be positive. Now see, this is 90-degree angle, this is another 90-degree angle. You will see this ODE will indicate an admittance triangle, and this OAE will indicate another admittance triangle. Sorry, phi is the angle between the real axis and the admittance. Now look at the second case, when BL is greater than BC. That means Y is equal to G plus J BC minus BL. As BC is less than BL or BL is greater than BC, therefore you see this resultant will be negative. Now see, to draw the admittance diagram, at first we will draw the conductance. This is plus X axis. In this direction we will take the conductance G. In this direction we will take BL minus JBL. In this direction we will take plus JBC. Now see, from the neat sketch you will see I indicated G with OA vector, JBL with OB vector, and JBC with OC vector. Sorry, this is minus JBL. JBC, as BL is greater than BC, so this resultant will be negative. That means at this point we have these two vectors are operating in opposite direction. As BL is greater than BC, so our resultant will be in this direction, and that will be J BL minus BC, because this is greater than this one. Okay, so to draw a parallelogram, from the neat sketch you will see I indicated that with OD equal to J BL minus BC. I can draw an equal vector of this one, that will be AE. This AE will be equal to OD. I can draw another equal vector from this point, that will be equal to DE. DE will be equal to G. Now see, if I draw a diagonal from this point to this point of this parallelogram, I will get the total admittance Y. Okay, so from the neat sketch you will see the angle between this real axis to the admittance will be negative, because we have to move in the clockwise direction. Okay, so phi is negative. Now see, this angle will be 90 degree, this angle will be 90 degree. This OAE and this ODE will indicate two admittance triangle, and this diagram is known as the admittance diagram of parallel RLC circuit when BL is greater than BC. And the third case is if this BL is exactly equal to BC. In that case, the admittance Y is equal to G plus J BC minus BL. As BL is equal to BC, therefore BL and BC will cancel each other. So admittance Y will be equal to the conductance G. Therefore, if I take this as our positive x-axis, our conductance G will be in this direction as Y is equal to G. So let's say this OA vector will indicate conductance G as well as admittance Y. Okay, that's it. Thank you.